All right, we are now recording. Let's get set up from the current slide. Any questions? Anything we've covered so far? Okay. You will see this or some very similar set of identities this chapter or this section, subsequent sections, probably in future chapters, okay? You'll see these over and over. These are important, folks. Okay, now remember all your test or take home, right? So I would have this already out there for me rather than having to search around in the book for them. These are worth writing down, okay? We went through the first several of these. We didn't have time to finish the ones at the bottom. So no questions on anything we've done so far? Let's hit these last. Do y'all all remember, let me get my pen activated in the right color, actually close as I can. It's on the top of page 282. Okay. Now, do you all remember, and this is one you use a lot, and it's really important to keep up with, what sine squared theta plus cosine squared theta is? It's 1 always, no matter what your angle is, the square of that angle, sine of the angle plus the square of the cosine of the angle is always, for every angle out there, equal to 1. That's an identity worth knowing and remembering. Now, what I'd like to ask you to do is divide every term on both sides of that equation by cosine squared. Okay, what does the first term give you? What is sine over cosine? Tangent, very good. Okay, so that would be tangent squared, right? And what is cosine squared over cosine squared? 1, always. And what is 1 over cosine? Secant. So this will be secant squared. You didn't have to memorize a new formula. You already knew everything in that. That's the same as this one right here. It's just another expression of that Pythagorean identity. The only little drawback to it, this is good for every angle theta in the world. Always. This is not, though. Why? Tangent and secant is not defined where. Okay. What did we just do to get here? Divided by cosine. What did you never divide by? 0. So the question is, where is cosine equal to 0? Cosine is your x coordinate, right? Think of the unit circle. Where is cosine is your x coordinate? Where is x equal to 0? On the unit circle. X is 0 up here and down there. What angle is up here? 90 degrees or radians. Pi halves. And what's the one over down here? Say again? 3 halves pi. So 1/2 pi, 3 halves pi, 5 halves pi, 7 halves pi, negative half pi. Your half pies. This is not defined at the half pies. This is defined everywhere. These are not defined at the half pies. But everywhere else, that statement's true. Okay? Now, going to ask you to do something else. Let's divide everything on both sides of that original equation by sine squared theta. Oops. There we go. Okay. And what's sine squared theta over sine squared theta? 1. All right, got that one. What is cosine squared theta over sine squared theta? Or, let me back off, cosine over sine. Cotangent. So this will be cotangent squared theta. And what's 1 over sine? Cosecant. So that'll be the cosecant squared theta. So there we have this one. Just right there. So these are the same 3 identities. It's just written in different ways. With one little exception. This one is defined where? All real numbers. Everywhere. How about this one? What do we do to get there? And what can you never divide by? Where is sine 0? No, that's your cosine. Sine is the y, right? And where is y equals 0? On the x-axis, right? And what 2 points of the unit circle on the x-axis? Yep, 0, pi, 2 pi, 3 pi. That's your whole pi's, not your half pi's, your whole pi's. I like whole pi's much better. Okay. Negative pi, negative 3 pi, negative 17 pi. Any whole pi, these are not defined. Okay? These are defined for everywhere except the half pi's. These are everywhere except the whole pi's. These are everywhere. Okay, the first one's everywhere. Now, they showed you these. I'm going to show you a few more, and I hope you'll agree with me, they're really the same things. But you tell me. Okay? I'm going to start again with our favorite one. In fact, I think I may erase some more. Let's go and erase some more. These are not listed in the book, but these are things you will run into, I promise you. I guarantee you, okay, you'll see these, okay? We're going to start with that one, our favorite one, right? Sine squared plus cosine squared is equal to 1. What happens if I subtract cosine squared from both sides? Then you have sine squared theta is equal to 1 minus cosine squared theta. Okay? Now, that's just written in a different form. It's also a Pythagorean identity, right? It's just you subtract, just like you divide it. You subtract the same thing from both sides. And you could do this as well. Cosine squared theta is equal to 1 minus sine squared theta. If you had subtracted sine squared from both sides, you would get that, right? Okay? Let's take one of these others down here. Let's this one subtract tangent squared theta from both sides. Now that time what we're saying here is secant squared theta minus tangent squared theta is equal to 1. Okay, there's another one. It's the same thing, it's just written in a different order. Or you could have subtracted 1 from both sides and had tangent squared theta is equal to 1, secant squared theta minus 1. There's another identity. Same thing with these two. Subtract cosine squared, cotangent squared from both sides, you get 1 is equal to cosecant squared minus cotangent squared. Or subtract 1 from both sides, you get cotangent squared is cosecant squared minus 1. And you can mix and match and move them around. There's a lot of Pythagorean identities. They all come out of this one and a few manipulations of it, but they're all there. So whenever you see the squares, think, is there a way to use this some Pythagorean identity to get what you want to get. Okay? So, now, a little bit of terminology here. Let me see if they print this on a slide or not. Yes, right here. when we say sine squared theta, what we're meaning is sine of theta squared. Sine of theta squared. But if I said that without writing it, sine of theta squared, you might think that was sine of theta squared. There is no identity for that. This is sine of theta in parentheses squared, so it's a lot easier and more precise and clearer to say sine squared theta. But that's what it means. Cosine squared theta means the cosine theta, that whatever that value is, squared. Okay? But we usually do this because if you say cosine theta squared, you don't know where the parentheses is unless it's written down for you. So saying it to keep the ambiguity out, we say cosine squared theta. Okay? Now, same thing with tangent, secant, cosecant, cotangent. Yeah. Tangent squared theta is the tangent of theta, that quantity squared. Okay. Let's move on to example 5. Let theta be an acute angle, okay, such that the sine of theta is equal to 0.6. Can, from just that information, you tell me what cosine theta is? Say again? And you can say, sure, I can, okay? How? Say again? I can't hear a little louder.
You have to plug things in.
Okay. How do you mean that?
Well, it gives you sine theta. It wants cosine theta.
Okay. So what you need is an identity that relates sine to cosine. Which identity will do that? You can use any of them you want to, but they have to relate sines and cosines. Maybe one. Ah, very good. We know that sine squared theta plus cosine squared theta is always what? Equal to 1. But we know what sine theta is, 0.6. So what is sine squared theta? .6 squared, 0.6 squared plus cosine squared theta is equal to 1. Yeah, we know that. Well, what is 0.6 squared? Sure you know. What is it? .36. 0.36 plus cosine squared theta is equal to 1. And where can we go from there? We're looking for cosine, right? There it is. Okay. So what do we do? Subtract 0.36 from both sides of the equation. Well, to do that, I'm going to put a 0.00 after the 1. And what does that give you? Cosine squared theta is equal to 0.64. Excellent. But I really don't care what cosine squared theta is. I want to know what cosine theta is. So how do I get that? Take a square root. And what's the square root of 0.64? Anyone know? 0.8. The book knew, didn't it? Okay, good for it. Okay. So yes, we can get that, cosine theta, just from knowing one piece of information, what sine theta is. Can we figure out what tangent theta is? Now, recognize now, it's not that we just know what sine is. If we just knew that, we're going to have a lot of work to do, because there is no identity that relates sine to tangent directly. But there is, if you know one other piece of information, sine and what is tangent theta? Quotient or ratio identity. Sine over cosine, of course, okay? And now we've already figured what that is, so this would be sine theta divided by cosine theta. These are identities, so you can use them anytime you want to, and that would be 0.6 over 0.8, because we just calculated that one. And what would that come out being? If you don't like dividing by decimals, move that one place over and that one place over. That's the same as 6 over 8. And what's that the same as? Just a reduction. 3/4. Or you could say 0.75. I don't care. Since the others are in decimals, this can be in decimal too. 0.75. Okay? Make sense? So you see, given one piece of information, using our identities, we can come up with lots of others. We came up with just knowing what sine theta was. We calculated what cosine theta was. We then used that to get what tangent theta was. I bet you could get what cotangent theta, right? That would be reciprocal identity. One over tan theta, and tan theta is 3/4. So its reciprocal would be 4/3. Fantastic. You can write that as 1.333 or whatever you want to do. I like 4/3 better. Could you get secant theta? The jar ends here. Could you get secant theta? Sure you could. How? 1 over cosine. And cosine you could have written as 0.8. You could have written that as 4 over 10, which is, 8 over 10, which is 4 over 5. So secant would be 5 over 4, 1.25. So yeah, you could get that one. How about cosecant theta? Could that be gotten? How? No, not 1 over secant. Wrong identity. Cosecant is 1 over, say again? Sine theta, exactly. So you could have written the sine theta as 6 over 10, which would have been 3 over 5. So cosecant would have been 5 over 3. You got them all. Once you have one, using Pythagorean identities, using any of your identities, you can usually come up with every one of them. Okay? It might not be pretty, but you can do it. Okay? Let's see how they did it. So let me first clear the slide here, and let's see how they did it. To find the value of cosine theta, what you have to do is find an identity that relates what you know to what you're looking for. You know sine, you want cosine. The only identity I know that relates those two is the Pythagorean identity. Sine squared plus cosine squared is equal to 1. That's always true, especially even when sine is 0.6. So plug that in. 0.6 squared plus cosine squared is equal to 1. That gives you cosine squared is equal to 1 minus, why don't we square it? 0.36. That would be 1 minus 0.36 would be 0.64. Then take the square root of both sides, and that gives you cosine theta is equal to 0.8. Okay. Now, let's go back just a moment here. They have left a little something out here. That's right here. Cosine squared theta is equal to 0.64. When you take the square root of both sides, it says extract the positive square root. There was not, yes it was. Let theta be an acute angle. If that had not said acute angle, then over here you would have gone plus or minus. But because in acute angles, everything, in the first quadrant, everything is positive. So you don't care about the negatives. But if they hadn't said that, then you could have had cosine theta is equal to minus 0.8, and that would have been cosine being the x value, that would have been over here. So You may have introduced more, but since it's at acute angle, we use only the positive. So we got it done correctly. And the tangent then was sine over cosine. Another identity, 0.75. Okay, and since you're dealing with acute angles here, if you drew this out, this was 0.8. You know that's 1. On the unit circle, that's 1 anyway. And then that would make this 0.6. Okay? Which would be the, I'm sorry, the 0.6 was the sine. That makes 0.8 the cosine. Look, obviously, this square equals that square. Pythagorean identity or Pythagorean theorem. They're the same. They come from the same source. Any question on that? Okay. Now, that was example 6. And by the way, every example then is followed by a checkpoint. I would definitely do these as soon as you can after class, at home, in the cafeteria, in the library, somewhere. Don't do it in another class if you pay attention in that class. But as soon as you get through, do it as soon so you can figure those out. And guess what? If you can't figure them out, by the way, that was example 5. They didn't do 6 or 7, so let's do example 6. All right. Let theta, yeah. Okay, example 6 is let theta be an acute angle. I can't spell it. It's U-T-E. An acute angle such that tan theta is equal to 1/3. Okay? Find the values A, cotangent theta, B, secant theta. Okay? They don't do a C. Okay. So if theta is an acute angle, first quadrant, you're staying in the first quadrant, not going anywhere else. So you don't have to worry about angles anywhere else. Find the cotangent of theta. How would you do that? What is cotangent theta? And you want to relate it to what you know. They told you tan theta. How is cotangent tan related? Get to know them. Are they related? It's been a long time since we went over those, hasn't it? How are tangent and cotangent related? Exactly. So if tangent is 1/3, what is cotangent? 3/1. 3, right? They're reciprocal of each other. Got it? What would secant theta be? Now, there's a couple ways you can do this. I know how they want you to, but I'll show you another way too. How do you reckon they want you to do it? You know tangent, you're looking for secant. Well, okay, 1/cosine, but where do you see a cosine on the board here? You don't. Now, you actually will be using it the way I tell you in a minute, but we don't have to do that yet. Okay? I'll show you a different way in a minute, but let's do it the way they want you to. How are tangent and cotangent, tangent and secant related? One of your identities. Pythagorean identity, which expression of the Pythagorean identity gives it to you? 1 plus tangent squared theta is equal to secant squared theta. Absolutely. Get to know them, okay? So this is 1 plus, what is tangent squared? If tangent is 1/3, what is tangent squared? Anybody? It's not that hard. If tangent is 1/3, what is tangent squared? Second? 1/9, of course, it's 1/9, okay? And that's equal to secant squared theta. Okay? Now, is it possible to add 1 to 1/9? How? What would that give you? Which is 9, and how many ninths is 1? 9 ninths. Okay, and what do you get when you add those together? 10 ninths, if my pen was right, is equal to secant squared theta. But you know I'm not really interested in what secant squared theta is. I'm looking for secant theta. So what do we do here? Take a square root. And since we're an acute angle, we're going to do the positive square root. And that would be what? The square root of what? 10 over 3. That's equal to secant theta. Done. There you have it. Now, that's how they wanted you to do it. Here's another way. I think nothing could be easier than to get the cotangent the way they said. Okay? But, based on what one of you said, that tangent was sine over cosine, right? Or, let's go back to Pythagorean. Well, yeah. Tangent theta is equal, remember our little acrostic? Opposite over adjacent, right? Remember that? So here we have our angle. I may be wacko with it here. Okay? We're told that this is 1 over 3. So guess what your opposite side is? 1. Adjacent side, this is your theta. 3. So to get your secant, what is secant? And one of you said it earlier, 1 over cosine. And what is cosine? Second? Okay, yeah, 1 over secant. I mean, in our little acrostic, cosine theta is equal to caught another hen, right? Okay, if you like ka better, ka is cosine is adjacent over hypotenuse. If you like that, fine. Okay, but sometimes my psi and my ka sound so close, I don't want to confuse you. So, but do you agree that's it? Adjacent over hypotenuse. Well, we got adjacent already. All we need to get is hypotenuse. Anyone give it to me? Can you give me the hypotenuse? What is hypotenuse? H squared is equal to? Anyone do that? It's not that hard. What's your hypotenuse squared? Name Pythagoras, ring the bell. Second. Okay. Isn't it a squared plus o squared? Okay. Okay. It's the finger writing. Okay. What did it come out being? What's your a squared? 9 plus is 10. So that's the square. So you take a square root. Was it that bad? Okay. Now, what is secant squared? Secant? You can either go from the definition. The definition of secant is 1 over cosine. Cosine is a over h, so this would be h over a. Right? And what would that be? Square root of 10 over 3, which is exactly the same thing we got here. Okay. So there's usually more than one way to get there. Okay? Whichever. If you like Pythagorean identities, use the Pythagorean identity. But if you also, and you're using Pythagorean theorem here, so it's the same type thing, but if you like messing around with the triangle, mess around with the triangle. When you're told tangent is 1/3, that tells you this angle has side 1, 2, 3. And then you can figure out what the hypotenuse is, and you can get all 6 of them, 3 functions. Sort of like that, right? Good deal. You could give me the sign. What would be the sign? No extra charge for this. They didn't ask for it. But what is it? What's the sign of the angle theta? Sock it to me. You like slide, I thought. What would that be? What is sine? Say again? Yeah, it is. But looking at the little triangle here, what is sine? Opposite over hypotenuse, 1/√10, which you could say is √10/10. Okay? What would the cosine be? Which would be? 3/√10, or 3√10/10. What? And we already know tangent, we already know cotangent, we already know secant. We just did secant. What is cosecant? So again, a little louder. √10/1. √10. Because it's just simply the reciprocal of sine. Sine was 1/√10, so it's 3/10/1. Good deal. See, you know them all. Give them one piece of information, you can get them all. Okay? Knowing the identities. Okay? Feel like a dentist here, pulling teeth. Okay? Let's clear that out of the way. And let's do example 7. Use the trigonometric identities to transform the left side of the equation into the right side. And what we're doing is using only acute angles, angles between 0 and pi/2. Okay, so here we have a sine theta times a cosecant theta, and they say that's equal to 1. Can you prove that for me? We're actually jumping a little ahead. We're going to be doing this in the next chapter, but this is real simple. Hint, use an identity. Hint, get everything as simple as you can. In other words, get everything in terms of sines and cosines if you can. The first factor is already a sine. Leave it alone. What is a cosecant? What's cosecant theta? From your reciprocal identity. Bless you. What is cosecant theta? Say again? 1/sine theta. Yes, ma'am. No, okay. They misnumbered that pretty badly. Yeah, no, it's all right. People do this. This is actually really good. Someone way back in the past did this. You know, this is 255. Even numbers are on the right, right? So if you go down there, you'll get 254, that's the English classroom. And the next one on the right, orientation classroom, is 256. They don't number the offices in between. So someone put up there 255A and 255B, because 254, 256, they did that. This is 255, those are not, you know, but that's why she was asking. She must be an online student, and she knew to turn it into 255, but she didn't know where it was. So, yep. All right, what did you say cosecant was? 1 over sine theta. And guess what that's equal to? 1. The signs go out. They've been dating. Okay, never mind. Okay. All right. That was the A part. Let's see about the B part. Ooh. Cosecant theta plus cotangent theta times cosecant theta minus cotangent theta is equal to 1. Now, where I guided you last time was say get everything in terms of sines and cosines. You can still do that here. But I would say unless it looks like there may be a simpler way. Okay? In this case, since this is a sum and a difference of the same two entities, you know what that comes out being, don't you? What is that? A little louder? Follett. Cosecant squared theta. And then if you did this, you get minus cosecant cotangent. You get plus cosecant cotangent. They add to 0, right? And then the last is minus cotangent squared theta. Supposedly, that's equal to 1. Is it? Yes, remember one of those forms I showed you of the Pythagorean identity when we had 1 plus cotangent squared theta is equal to cosecant squared theta? Right? And I said subtract cotangent squared from both sides. And what does that give you? 1 is equal to cosecant squared theta minus cotangent squared theta. And that's exactly what we got here. So yes, that checks. Right? So the right-hand side is, left-hand side is equal to the right-hand side. So in this case, I wouldn't do sines and cosines. Most of the time, that is my first step. But when you got something that's going to simplify like that one did, go for it. As soon as you get the squares in there, think Pythagorean identities, go look around. Ah, yeah, that works. Now, they probably do it a slightly different way. No, they don't. They do it exactly that same way. Okay, again, there's a checkpoint after this. Do it as soon as you can. Any questions on that? All right. Now, applications involving right triangles. Okay? Many applications of right triangles involve a process called, many applications of trigonometry involve a process called solving right triangles. Strange kind of name. Usually you solve equations. What do we mean by solving right triangles? Well, we identify the equations they give us, okay, and solve. This type of application, you're usually given one side of a right triangle and one of the acute angles. If you're given that, you're asked to find one of the other sides, or you're given two sides and you're asked to find one of the acute angles. One way or the other, okay? That's called solving the right triangle. Because guess what's always true in a right triangle? Always true in a right triangle. Say again?
It's got a 90-degree angle.
That 90-degree angle is always there, okay? What does that tell you about these two angles? To add up to equal 90, that makes them? Yeah. They're called what? Okay. If they add to be 90 degrees or pi halves, you call them. Oh, your hair's nice today. Complementary angles, exactly. Okay. Complementary angles. Okay. That was neither here nor there. What do you know about the sides of a right triangle?
The hypotenuse is always longer than the
Okay, you got that right. The hypotenuse is always longer than either of the other two sides. What else you know about it? That's qualitative. Give me a quantitative. There's only three of them. That's quantitative. Okay, and a triangle. Yes, I think we got that down. Okay. What relationships do those three sides have? It's right there in front of you.
I have no idea.
Doesn't that Pythagoras ring the bell? What does that tell you?
A squared equals C squared.
Exactly. X squared plus A squared is equal to X squared plus A squared. So this side here, the hypotenuse is the square root of that. Okay? Pythagorean identity. Only we were calling this calling this O and A. And that's the H is that. So yes, you know lots of things like that. Okay. Now just a few definitions. In example 8 that we're going to do next, the angle you're given is called an angle of elevation. What does this mean? If you're standing on a level base from something and looking at the top of it, that's the angle of elevation. From the horizontal to the top, that's the angle of elevation. If you're looking from up something, down at something, it's called an angle of depression. Okay? Also from the horizontal. Always from the horizontal. Okay? So the other application may be given an angle of depression, which represents from the horizontal the angle downward to your object. So that would be like if you're in an aircraft and you're going to drop a bomb you're going to drop some supplies to somebody. That's the angle of depression. Okay. Never mind. You were listening. Okay, got it. Okay. So that's the type of problem we're going to use. Here is an example of this. A surveyor is standing 115 feet away from the base of the Washington Monument, shown in this figure, and he has a sextant with him, and he's measuring the angle to the top of the monument. Okay? Finds that to be 78.3 degrees. Okay? Can he calculate how tall the Washington Monument is without climbing up? We hope so. How? Draw a picture. Fortunately, they already drew a picture for you. Put the things in here. This is what we're looking for. What we know is how far he is from the base, and we also know the angle of the elevation. Now, if you've ever been to Washington, D.C., around the Washington Monument, you know it's a pretty flat area. The reflecting pool, everything is pretty flat there. I hate to use this phrase, they filled in a swampy area there, and that's where they built the District of Columbia. So everything's pretty flat. They flatten everything out pretty much. Okay? So, if you know this angle, and if you know that length, what are you looking for here? How does this side and that side relate to this angle? And guess what? The other assumption here. Number one, that you're level. Yeah, we're okay with that. Number two, we assume the Washington Monument stands straight up. Okay? So that means this would be a 90 degrees. Exactly. So, what does that tell you? If that's 90 degrees, what side would you call this one? There's your angle right there, your 90-degree angle. Kind of put that in there. That's your 90-degree angle. This would be called your, for this angle, 78.3. This is the side adjacent to that angle, and this is the side opposite that angle. So what relates this angle to these two sides? Yeah, trig function, because we're doing trig. Okay? Tangent, yes. What do you say? Say it again. Tangent of of theta is equal to opposite over adjacent. Now, which of these is which? Opposite is the y, and the adjacent is the x. Very good. So what do we have? Let's write down what we just said. Tangent of, but we know what theta is, don't we? Don't we? Yeah. What is it? 78.3 degrees. Tells you better get in degree mode, folks. What is the opposite? Y. We don't know that. That's what we're looking for. And what's the adjacent? 115. Okay, I want to know what y is. So I'm going to multiply both sides by 115. And by the way, that's in feet. Okay, I'll wipe out the 115 here, and y is equal to 115 times the tangent of 78.3 degrees. Now, you all have calculators, right? What's the first thing you better do before you try to solve that? Make sure you're in the right mode. What is that? Degree mode. Now, probably every one of you has a different calculator. You have to know your own calculator. You have to know how to get in degree mode. Get there. Once you're there, 15 times tangent of 78.3 degrees. Now, you have to know your own calculator. Some of the old calculators, like scientific calculators, you are required, once you're in degree mode, you put the argument in first, then you put the function. And most of the newer calculators, the display type calculators, the graphing calculators, you can just type it in as you do it. 115 times tan, the tan key, if you're in degree mode, 78.3, that should give it to you. What do you get? A little louder? Anyone get anything? Got a calculator, didn't you, or is that a phone? That's a phone. Okay. What's that? Oh, I see. Actually, on most of the phones, you have a calculator mode, but there's also an advanced, or I can't think what you call it, mode that you can actually do sines and cosines. I don't know if yours will, but a lot of them can. Huh? Boy, these black boxes sure slow you down, don't they? Okay. Can you get there from here? Huh?
Is that 78.3?
Yeah, tangent 78.3 degrees. I know you were following along in the book. Huh? What's that? Okay, 500 and what? 535, is that what you said? 55? Okay. Isn't there another digit?
Yeah, 555.
Oh, 555. Okay. Okay, that would be feet. Okay, let's see what the book got. Yeah, 555 feet. Very good. Now, I'm okay with that, especially since they only have 3 digits here, 3 digits there. The closest 3 digits looks good to me. Okay. Anyone can't figure out how to get there from here? Okay. I can see if I can help depending on what you got. Is it a calculator or a phone? A calculator. Were you in degree mode? Okay. Mode. Here's the mode key. And goodness gracious, this is anything else. Okay, maybe it's not degree. I mean, that may not be. Let's see. Instead of math, get it in the degree mode, or was it already there? Okay. Yeah, you'll have to get your book on this one to see how to get it in degree mode. But what she did was just type it in. I'll let you do it. Get back to this. Clear that if you want to. Okay. I'll do 10. Right there. Put 78.3. Press equal. That should give it to you. You really should. Now, that's in degree. Somehow your calculator has to be able to get to radian mode. I don't know on yours how to do it. Most of the time there's something that tells you. Let me see. Let me look at your calculator. This is degree, radian, gram. Okay. So if you do the yellow key is your shift, then that gives you degrees, radian, or gram. So you're already in one. So you're in degree mode. So that's right. And if you never did radian, that's where you got that key is fine. Okay. All right, good deal. Any more questions on example 8? Let's see how they did it. They said tangent of 78.3 degrees is opposite of adjacent from their picture. Folks, they drew the picture. Always draw a picture if it helps, and most of the time it does. Pictures are worth thousands of words. They'll help you see relationships, okay? And that's going to be, in this case, your y over the x, where y is the height. X was the distance from the base. So you plug that in, x equal 115, y is the height, that's what you're looking for. So if you did that, then you get y is equal to x times the tangent of 78.3, plug in what x is, and that gives you, and they figured out what the tangent of 78.3 is, 4.8, blah, blah, blah. And when you multiply the go, you get approximately 555 feet. Okay. Now, I don't know if you know this, but no building in the District of Columbia can be more than that high. So that's why you don't find any skyscrapers there. Okay. At least in the capital area. Now, maybe outside of, I don't know, but supposedly no building can be any taller than that. Okay. By now, you're able to recognize the fact that if theta is equal to 30 degrees, what is it? That's the acute angle that satisfies what would be what? Can you tell me about the sine of that 30 degrees? Oh, that was last week. We weren't supposed to remember that anymore, were we? What's the sine of 30? Remember a little trick I told you? Okay. Yes, oh, you read well. Okay, excellent. 1/2. Very good. Remember how we did that? Remember those angles that we really like to remember. 30 degrees, 45 degrees, 60 degrees, and of course 90 degrees. Okay, and this of course down here is 0 degrees. Okay, okay. For each of those, this opposite side is, for 0, it's 0 over the square root. No, it's the square root of 0 over 2. This one is the square root of 1 over 2. This is the square root of 2 over 2. This is the square root of 3 over 2. and this is the square root of 4 over 2. Okay? Well, of course, square root of 0 over 2 is 0. Square root of 1 over 2 is 1/2. Square root of 2 over 2 is square root of 2 over 2. Square root of 3 over 2 is square root of 3 over 2. And the square root of 4 over 2 is 2 over 2, which is 1. Okay? So that's the sign of those 5 angles. 0, 30 or pi 6, 45 or pi halves, or pi fourths, 60 or pi thirds, and 90 or pi halves. That's the sign of those 5 angles. Okay. Suppose, however, that you are told, given the equation, sine of theta is equal to 0.6. Well, you know sine of 30 is 0.5, right? 1/2 is 0.5, right? So if you were told sine of theta is 0.6, and we're asked to find the acute angle, because you know that sine 30 is 1/2, which is 0.5. Sine of 45, from here, you know it's 1 over root 2. See, I told you earlier they were writing this as square root of 2 over 2. Now they're writing as 1 over 2. It doesn't matter. It's still 0.707. So guess what? The angle that's in between these two sines has to be an angle in between those two angles. So I'm going to guess around, 37, 38 degrees. Okay? Somewhere in between 35 and 40, 30 and 45 degrees. 37. Okay. Somewhere pretty close to that. I knew it was that, but I wanted to say it's something in between those. Okay, good deal. Now, they're skipping example 9. Let's us not do that, okay? Well, let's see. Let's find the place we can write. Like maybe right here. Example 9. A historic lighthouse is 200 yards from a bike path along the edge of a lake. A walkway to the lighthouse is 400 yards long. Find the acute angle between the bike path and the walkway as illustrated in this figure. Okay? So let me do something a little different here. Okay? And I'm going to let this be the edge of the lake. We're going to assume it's a very straight beach there, like the picture is here. And here's the bike path right along the edge of that lake. So there's your bike path. And we know the lighthouse here, with the light in it and stuff like that, that is 200 yards from the bike path. Straightest distance. 200 yards. Okay. However, you know that the walkway they did was 400 yards. Okay, 400 yards. Find the acute angle theta between the bike path and the walkway. That's what we're looking for, folks. That angle theta. Now, remember I said you assume this is shortest distance to the path, 200 yards. So they put the walkway 400 yards at an angle there. What is that angle? This is shortest distance. That, by definition, is your right angle. Shortest distance is the perpendicular distance. So we're assuming this is a right angle here. So what can you tell me about this angle theta and these two measures here? What is the relationship? The trigonometric relationship between those. Earth to class, come in please. Okay, if that's a right angle, this is the angle in question. What is your 200 yards in relationship to that angle? That's your opposite. This is your opposite side. What is the 400 yards in relationship to that angle and your right angle? That's your hypotenuse. And what trig function relates an angle to its opposite side in hypotenuse? Sock it to me, babe. Say again? Sine. The sine of theta is equal to what? Opposite, which is 200 over hypotenuse, which is 400. Now, time out here. This only works if you have the same units. If they are given one of these in feet and one in yards, don't mess with that until you get the feet in the yards or the yards in the feet. Get the same units. They were nice to you. They gave you the same units, okay? So you're fine. And what does that reduce to? Does that reduce at all? 1/2. Well, if you know the sine of theta is 1/2, I think you can tell me what that theta is, can't you? You better. We just did it. 30 degrees. This is 30 degrees. Or if you put it in radians, that would be pi over 6 radians. Okay, 30 degrees or pi 6 radians. I think they got it right. Okay? It can't be, can it? Oh my goodness, how could it possibly happen? Okay, somewhere here, before you go anywhere, I have a pencil somewhere on my desk. There it is. We will start next time with example 10. Okay, we've done 9. Homework exercises here, folks. Don't go anywhere. I've got to find my piece of paper. There it is. Homework exercises here. You know what it is. Do either 5 or 7, either 9 or 11, any of the odds 13 to 19, any of the odds 21 to 29, any of the odds 31 to 39, any of the odds 41 to 45, any of the odds 47 to 55, any of the odds 57 to 61, do either 63 or 65, and then try to do any of the odds 67 through 77. If you can't get them all, we'll do at least one more example next time. Answer any questions. Good deal. Any questions? We'll see you Thursday.